Won't be a ton. Give you guys time to work on the homework afterwards, so hopefully less to do Sunday, right? All right. So what we want to remember from geometry is we talked about types of transformations. You guys talked about translations, talked about reflections, and dilation. So when we talk about a translation, that's like just changing the location of an object. So if I have a square here, we could shift it like to the right 5 and up 7, and it's just the same shape, same orientation, and just add a new location, right? That's what we mean by a translation. A reflection would be like, say we have a square here and we flip it across some line. So it, again, it just changes kind of the location, but it's like a mere reflection of itself. Now a square has like no symmetry or whatever, but if you had like a triangle where, you know, the vertex was pointed to the right, when you reflect it across, the vertex would point to the left. So you have some change in orientation possibly. And then a dilation, which is like a stretch or a shrink, which again, like if I take a square and I like stretch it, it's just going to be like a bigger square, and like the orientation of it should stay the same, right? The way it's pointing. But like the size of it's going to change, and like the location of the vertices are probably going to change unless they're like 0, 0 or something. Yeah.
What was the translation?
And just picking up and moving. So you can do that. We can have these same transformations to any set of points, right? Everybody's okay with that idea? You guys would have talked about this in geometry. So if we think about this now algebraically, a function is just a collection of points, right? So I can take the same idea of these transformations from geometry and kind of apply them to a function. So the language we use, we call the starting function our parent function, and typically what I'm just going to name this is just y equals f of x. And typically the parent function is like the simplest version of something. So for example, if we're talking about the set of quadratic functions, you know, like x squared would be an example of a parent function for quadratics. It's like the simplest version of a quadratic. Or if you're talking about like square root functions, maybe you'd say x equals the square root of x. Would be like the simplest version of a square root function. Or where we're heading, like y equals sine x, which would be like the simplest version of a sine function. Yeah. What's up? Oh.
So the parent functions are just like the simplest version.
Mm-hmm. Yep. So when we perform a transformation to some parent function, we call that the resultant function. Yes.
What are the parentheses?
End. Right? Like we have the start, or we start with the parent function, we do some kind of transformation, and we have an end then. Yeah, what's up, Vlado? Oh.
How'd it go?
Seemed good. I think everybody got everything needed. Right? So, yeah, you're welcome. We'll do it this way. And we'll write it that way. How's that? So the way we write our resultant function generally is this. So y equals a times f of 1 over c times the quantity x minus h plus k. Now, these coefficients a, c, h, and k are going to describe to us what type of transformation is occurring. So each one of them controls a type of transformation, and depending on what the number is, will tell us kind of what's happening. Okay? So let's list what those are. So the first coefficient we talk about is c. So if c is less than 0, what does that mean? It's negative, right? That's just another way of saying it's a negative. It's going to reflect our function across the x-axis. And if it's positive, the c does no reflection at all. Can it be 0? No, right? Because if it's 0, you have 1 over 0, and that's broken math. Okay, well, c actually controls the reflection across the y-axis, but it controls another thing also. It says that if the absolute value of c is bigger than 1, we have a horizontal stretch by a factor of c. So when I say a horizontal stretch, it's like if we had our square and we grabbed the sides of it and we pulled it like that way. Kind of makes it look more like a rectangle, like a wide rectangle. If that c value was, our absolute value of c is less than 1, what's an example of a number that's the absolute value of it's less than 1? Okay. What else? What? No. What's an example of a number whose absolute value is less than 1 other than 0? Not a negative necessarily, because like the absolute value negative 3 is 3. Like 0.5, a half, a third, a fourth, 4/5, 7/9. All of those things have absolute values of less than 1, even whether they're positive or negative, right? Well, fractions that are less than 1, where the denominator is bigger than the numerator. In that case, there we have a horizontal shrink, again, by a factor of c. And if c is equal to 1, no dilation is happening. So c can do two things, right? It can reflect across the y-axis, and it can cause some kind of horizontal dilation, a stretch or a shrink. Dilation is just our generic term that means either kind, right? Stretch or shrink. So then we talk about the a's. If a is negative, we reflect across the x. And if a is positive, there's just no reflection. But just like C, A can do something else other than just reflecting. So if A is greater than 1, we have a vertical stretch now. If the absolute value of A is less than 1, we have a vertical shrink. And if it's strictly equal to 1, we have no dilation. Next, we're going to look at the H. So if the H value is, just say, don't need that, is positive, we're going to shift right H units. If H is negative, we shift left H units. And if H is 0, we do nothing at all. And then the last one is the K, and the same kind of thing, except it's up and down. Okay. So this stuff you're going to use a whole bunch. If you don't memorize this, definitely note card material right here, right? Now, honestly, you'll probably use it enough that you'll have it memorized, but if you're memorization is not my strength, that's prime note card material right there. Let's do an example here. So let's say we have y equals f of x as our parent function. And then let's say that y equals negative f of 3x minus 6 plus 5. And what we want to do here is we're just going to identify the A, C, H, and K, and then describe the transformation words. Okay? That's our goal here. So to identify the A, C, H, and K, I need to write my function that I'm given in that form, right? So I can see probably pretty clearly that the A is -2 and the K is 5. But the middle part isn't exactly written in a way that I can pick out what the C and the H are. Everybody kind of see that? So what I'm going to do is I'm going to start by doing some algebra inside that parenthesis to make 3x minus 6 look like a 1/c times x minus h. Everybody okay there? In fact, I'm going to make this, I want to make that plus, just to make it a little bit, cover all my bases. Okay? So what I'm going to start by doing is I'm going to look at this 3x plus 6 and try to write it in a factored form. So do you guys see anything in common between the 3x and the plus 6 that I could factor off? 3, right? So if I factor 3 off, what am I left with inside? X plus 2. Everybody okay with what I just did there? Now notice we still have a couple of problems because, well, that 3 needs to be written as like a 1/c. And then that plus 2 is supposed to be like a minus h, right? But we're getting closer. How can I write c as 3 as 1/c? Well, if I think about 1/c as the reciprocal of something, right? That's the reciprocal of c. The reciprocal of what number gives me 3? You mean 1/3, right? The reciprocal of 1/3 is 3.
Yeah.
So I'm going to write this as 1/1/3. Everybody's okay with that? That's basically like doing 2 reciprocals, which is the same as doing nothing at all, right? Still just 3. Now, how am I going to write that plus 2 with a minus in front of it? Well, addition is the same thing as minus a negative, right? So I'll just write that as minus -2. So now let's look at what we have. The A, that's going to be -2. The C is 1/3. The H is -2. And the K is 5. Ava. Okay. This skill that we've just done is like core to being able to do most all of the problems from chapter 3 correctly. So that skill that we just performed is like a foundational skill for like almost everything we have to do in chapter 3. So it's critically important that you're able to get the values of A, C, H, and K from looking at an equation. Okay? That you're able to kind of break it apart like I did here to get the values. Now that wasn't too difficult, but you have to be able to do that. Now what we want to do is we want to write the transformation in words. So the first thing we do is we look for the C's, right? I notice that my C is positive, so that causes no reflection. And then the absolute value of C is less than 1, so I have a horizontal shrink by a factor of 1/3. The next thing I do is I look at the A. Since I notice the A is negative, I have a reflection across the x-axis. Since the absolute value of A is greater than 0, greater than 1, we know we have a vertical stretch by a factor of 2. Since our H is negative, we're going to be going left 2 units. And since our K is positive, we're going to shift up 5 units. Everybody okay with what we did there? I just used the criteria that we wrote up before, using the numbers that were the values for my specific A, C, H, and K, right? Ava?
What's the stretch?
That's a V.
Oh.
Yeah, it's supposed to be the letter V. I try to always put a tail on my U's, at least when they're at the start of a word anyways. But yeah, it's supposed to be a V. Okay. No big deal there, right? What if we change this problem a little bit, and this time we say our f of x is x cubed, and our resultant function is two times x plus 1 cubed plus 4. So again, I know if y equals f of x, I can get my a, c, h, and k by just rewriting my function in that form, right? So here, my parent function is x cubed. So the f in this case is going to be something cubed. So where the f was in my function, I've just replaced by cubed. Is that okay with everybody? All right. So let's now rewrite this so that our function 2 times x plus 1 cubed or plus 4 looks like that a times 1 over c x minus h cubed plus k. So what is, is there anything in common between the x and the 1? Just a 1, right? That's the only thing I could factor out. So the c I'm just going to write as 1 over 1. then what was the trick I do to make that positive? Yeah, as I think about it as a 1 minus, or a minus -1, excuse me. So if I look now, let's see what we got. A is 2. C is 1. H is -1. And K is 4. And I'm going to omit the writing part for this example. Is that okay? I'm just going to do the find the AH or ACH and K, because that's the part that's going to be, tends to be the trickier part. Using the criteria is literally just a case of like, okay, which one of these, does this fall under? So far, so good? Okay. New example. So suppose we have the function x squared minus 3x, and that's our parent function. Okay. So this tends to be maybe the most challenging question we do from this set of topics. So when I read this, vertical stretch by a factor of 2, what is happening? Which coefficient are we talking about? A, C, H, or K? So if you go back to our list, we're looking for vertical stretches, and that happens with A's. Great. So here, I know that the A is going to be 2, but everything else should be just something that doesn't change. So C is the thing that doesn't do it, or 1 is the number that makes C do nothing. H is the number that makes, or 0 is the number that makes H do nothing, and 0 is the number that makes K do nothing. So what I do then is I say, okay, my new function, g of x, is going to be 2 times f of 1 over 1, x minus 0, plus 0, or just 2 times f of x. I'm going to call this g1 because it's on our first transformation that we're doing. Okay, and the f of x in our problem is x cubed minus 3. Or I'm sorry, x cubed minus 3x. So then I can just distribute the 2 through. And we're done with step 1. That's our intermediate step. That's what our transform function is after we've shifted it or done that vertical stretch to it. Everybody's okay? Now we're going to move to step 2. Shift left 3 units. A, C, H, or K. Which one are we talking about there? It is H. And what value should H be then? -3. Good, because we're going left. That's the negative part. And then the 3. And then everything else should do nothing at all. So for A and C, 1 does nothing. And for K, 0 does nothing. So for step 2, my transform function I'm going to call G2 is going to be 1 times G1, 1 over 1 of x minus a -2 plus 0. Or just G1 of x plus 2. So we had, this is our, we're eventually going to end up at G3, right? This is just the name I've given to my transform function. So after G1 was the transformation of f of x by that step 1. G2 is going to be what we did last time, but doing this new translation to it. So we're just taking our answer before and transforming that. So I'm just going to have, like, for each step, it's going to be a new number G. Ava.
So these problems are just like taking the horizontal function and doing these random steps. Like you could come up with any steps on the list.
Correct.
You just picked 3 random.
I just picked 3 arbitrarily.
Okay, and then for like the H equals, so it was like H equals 0. Do you add or multiply like the 3 units to that?
H doesn't equal 0.
It's like separate.
It's.
To that one. Oh, but like it was, wait, H equals -1, so you just multiply.
H didn't H equaled -3.
Yeah, but like in the other equations,
H was 0.
there's 2 separate.
We're doing 2 separate, we're doing 3 separate transformations, right? We're doing it, rather than trying to do stuff all at once, we're going to do it 1 step at a time here. So I'm just going to do the first thing to it, and then we're going to do the second thing to it, and then we're going to do the third thing to it, because it says that we're performing these transformations. So we need to go in the order that they're listed. If we try to do it all at once, it's not going to be in this, it's not going to be the same result. Okay. So I have then, if I do G1 of x plus 2, what is that going to mean? Is everywhere there was an x, I'm going to be plugging in x plus 2 into my G1, right? It's like a composition of 2 functions like we did in chapter 1. So everywhere there was an x, I just replaced it with an x plus 1 or x plus 2. Is everybody okay? Now I'm just going to simplify this. So when I simplify x plus 2 squared, what do I get? You mean x plus 2 times x plus 2? Yes. You have to FOIL that out. Yeah. Good. Yes. So I'm going to do that quickly here in my head, but that was what I wanted to check for us to make sure that we remember that that's a FOIL step and not a x squared plus 4. And then we'll just distribute things through. and then we'll combine our like terms. And that is our G2. Certainly. What can't you read, Ava?
Oh, it's -12.
Yep. Okay. Once we've done that, now we're going to go back to our final step. Our final step says to reflect across the y-axis. So is that going to be A, C, H, or K? Again, we'll go back to our list of criteria and see where reflect across the y-axis came from. And it comes from C, right? So the C value, if it's going to be a reflection across the y-axis, must be negative, but it doesn't tell us exactly what number it should be. But because it's not telling us there's another horizontal stretch or shrink, we know that the absolute value of C has to be 1. So in turn, we just have that C has to be -1. And then the others can't do anything. So when A doesn't do anything, it's 1. When H and K don't do anything, they're zeros. And we're ready to now plug that into our formula again. So G3 is going to be 1 times G2 of 1 over -1, x minus 0 plus 0, or just G2 of -x. Feel okay? And now this looks just like our odd-even thing, right? When we would do like f of -x and see what we got. So much in the same way the previous problem, I'm going to be taking my -x and plugging it into the x's in G2. So -x squared is positive x squared. 2 times -x is -2x. And then the 4 just stays, or the -4 just stays -4. So this is our final answer. That's our new, or our resultant function after the 3 transformations. I'll just call that G then. Okay. So let's think back to geometry. If we have some point in the parent function, some xy, and we have some transformation, the point in the resulting function can be obtained by doing c times x plus h, and then a times y plus k. This is another thing, again, that's super important. You're going to use that a ton. It'll make life massively easier for you when it comes to graphing our trig stuff, if you remember this transformation map. So this is something, again, I would memorize or certainly go onto my note card if I don't feel like memorization is my strong suit. So let's say that our parent function consists of the following points. Actually, this is an example. Let me move some stuff around and make the format a little nicer. Okay, so let's say an example. All right, so let's say we have the parent function f of x with defined by the points here below. And we want to take and then we want to be able to graph this new resultant function, which is 2 times f of x plus 3 minus 1. So my first order of business is to figure out my values for a, c, h, and then k. So if I look at this, or if I go back and remember my general form for a transformation, looks like that. So what is my value for a going to be? Who can tell me? It should be 2. What should the value for C be? What do we notice there?
0.
Not 0, because what's the coefficient there? 1. Yeah. Okay. And what's the H going to be? What's that, Colin? Which one is it? It's not -1, it's -3 though. And then the K should be not 1, -1. Is everybody okay with how I came up with those values? Again, the most common mistake students make, and it gets like a whole graph wrong, is when we can't come up with our values for A, C, H, and K consistently, right? The H's are tricky because they're always kind of the opposite sign of what it looks like. The C's are tricky because it's like the reciprocal of what you think it's going to be. But you just have to kind of go slow through it. So my transformation map is then going to be 1 times x plus -3, and then 2 times y plus -1, or just x minus 3, 2y plus 1. So -2, 0, I'm going to plug -2 in for x because it's the x coordinate, and plug 0 in for y because it's the y coordinate. So that becomes the point -5, 1. And then I'm just going to do the exact same thing. as I move through the rest of these points. I'm just plugging the point. So like the x goes in for the x, and then like the y goes in for the y. And I'm just going to do that for every xy. Yes, certainly. Yeah, of course. Oh my goodness, Mr. Kulik, you are such a dumbo. Plus a -1 is minus. Those are all supposed to be minuses. Ay, ay, ay. Minus, minus, minus. 0. -5. Oh, I'm sorry, not 0. -1. -5. And then -1. Ay, ay, ay. And we have 1, 7. Okay. That's the gist of what we're going to do today. Next time we're going to take these same ideas and apply them to sine, cosine, tangent functions. So we're going to see what the graph of those things look like, figure out what these points for the parent function should be, and then start graphing transformations of them using this exact same method that we've outlined here. Okay? For homework for what we just did, I'd like you guys to do this worksheet 1 here. The first page is already kind of just some summary of notes. The second page asks you to describe the transformations in words. So it's just like identify the values for A, C, H, and K, and then say, oh, it's a reflection across the x-axis and blah, blah, just like that stuff. And then the next 2 pages, you're going to be graphing. So the parent function in all these cases is going to be x squared, and the points that we should use on x squared, so these will be like the points for your parent function. So to do it just like we did in that last example, those should be the 5 points you're using. So -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Okay? So this will be part of Sunday's problem set. We have about, 30 minutes left here today. Should be able to knock out a big chunk of this right now. Obviously, start at the part where you feel the least comfortable. So that if you run into snag, you can ask some questions about it and get some clarification before you're stuck doing it on your own. Okie dokie. Okay. Very good.